In this segment, we're going to examine a procedure in which we take an algebraic fraction and we rewrite it as the sum of two or more relatively simpler fractions. Well, the simpler fractions are called partial fractions, and the process is sometimes called partial fraction decomposition because we are decomposing the original fraction into the partial fractions. Here's how the process works. We start with a fraction that might look like this, and we begin by factoring in the denominator. Now, it turns out that the two partial fractions will have as denominators the separate factors that we have here. So one of them will have this factor and the other will have that factor as a denominator. Now the trick is to identify the numerators of these fractions. We'll identify those numerators as a and b. Now let's clear the fractions here by multiplying through by a common denominator. The common denominator would be the product of these two factors, and when we multiply these two factors in this term, we get simply 5 after the cancellation clears these factors. When we multiply x minus 3 times x plus 2 times this fraction, the x minus 3's cancel and we have a times x plus 2. When we multiply x minus 3 times x plus 2 times this fraction, the x plus 2's cancel, so we have b times x minus 3. Now, we still want to identify the values for a and b, and we do that by actually eliminating one of these terms or the other, and we can do that by letting x take on some very particular values. You see, what we've done here is we've set up a rather peculiar kind of equation called an identity. And you may recall that an identity is that kind of equation which is true for all real number replacements for x. Identities are often used in the description of properties, like the distributive property can be illustrated by using an identity. Well, we set up an identity right here, that this fraction is equal to that fraction for all x, for all values of x. You see, that's the idea. Okay, now, if that's true, then we can let x take on values that will cause each of these terms to disappear. For example, suppose we let x take on the value negative 2. You see, negative 2 plus 2, this term goes out. So now we have an equation involving only b, and x has already taken on this value, so we can solve for b fairly easily. So we have 5 then is equal to negative 2 minus 3, that's negative 5, so negative 5b. Dividing on both sides by negative 5, we find b to be negative 1. And now let's cause this term to disappear. We would let x take on the value 3. This term goes out, and we would have, well, let's see, 5 on the left, and then if x is 3, 3 plus 2 is 5, so this would be 5a on the right. Dividing by 5, we find a to be 1. So b is negative 1, a is 1, and we can write our fractions up above here as, let's see, the a value is 1, so we have 1 over the x minus 3, and then plus negative 1 for b over x plus 2. And because we have this negative 1 in this numerator, we would probably end up writing this as, so you just swap signs here, we would have minus 1 over x plus 2. Well, it's possible to check this partial fraction decomposition process, our answers in this, by using the graphing calculator. Let me show you the technique for doing that right quick. The first equation, y1, is the left side of our equation, the fraction on the left side of our equation that we saw a moment ago, and this is the right side of the equation. All we're going to do is verify that the two graphs of these two equations are identical. They just lay over one another. It might be helpful in doing that to deselect this first one. I'm pressing enter here and deselecting that equation for graphing. Here's the graph then of the first equation. So that left side fraction has a graph that looks like this. We want to just verify that the right side fraction has exactly the same graph, and therefore the equations would be equivalent. Well, I'm going to select now y2, and now both graphs will show up. Gee, we don't seem to see any difference. Well, that's good news, because it means that the two graphs are right on top of one another. To further verify the idea, we can press trace, And we can just jump from one graph to the other. Now notice the equation is written in the at the upper part of the screen with coordinates at the bottom part, but when I press either the up or down arrow button, I'll jump to the other equation, you see. And so we're just jumping from one graph to the other graph, one equation to the other equation, and therefore the left side expression has exactly the same value and is equal to the right side expression, and that's what we're verifying. In this example, the fraction to be decomposed is a little bit more complicated, but that's not a big deal. We follow the same procedure that we did before. It is important, though, to notice that the degree of the numerator is smaller than the degree of the denominator. Now, that is an important consideration. As long as that's the case, then we're okay following this procedure. All right, the process is to factor in this denominator. We snag out a common factor of x, and it would leave x squared minus 1. Then we factor that difference of two squares into these three factors. All right, so away we go. We set up our partial fractions according to the factors that we see here. We have one partial fraction for each of these factors. So we have this arrangement. Now notice that the numerators now are a, b, and c, and the trick is to identify those values. All right, we clear the fractions by multiplying through by a common denominator. The common denominator would be the product of all three of the factors here. When we multiply the common denominator times this fraction, the denominator factors will cancel, leaving the numerator. And over here, when we multiply these factors times that fraction, the x's go out, leaving these two binomial factors times a. So that's what we have here. Then these three factors times this fraction, the x plus 1's go out, and we have x times x minus 1 times b. And then these three factors times this fraction, the x minus 1's go out, so we have c times the other two factors. Now we want to choose, cleverly, values of x that will cause various terms to disappear. Now notice that in this arrangement of factors and the terms that a couple of terms share factors. That is, these two terms have x minus 1 factors in them. These two terms have x factors in them. And these two terms have x plus 1 factors in them. So if we want to find the value for a, then we look at shared factors by these two terms. And these two terms share the x factor. So if we let x take on the value 0, these terms will go out. Let's do that. Let's let x equal 0. All right, over here, these two terms will disappear, and we have negative 2 equals, let's see, on the right, those two terms are out of here. If x is 0 here and here, we have negative 1 times a, or simply negative a. And a then is 2. All right, that was easy enough. If we want to find the value of b, then we look at the factor shared in these two terms, and it's x plus 1. So we would let x take on a value that will cause that shared factor to become 0, and the value then would be negative 1. So let's let x be negative 1. On the left, negative 1 squared is 1, times 3 is 3. Negative 1 times negative 7, 7. 3 and 7, 10. 10 minus 2, 8 on the left. All right, let's see. This term disappeared because when x is negative 1, we have a 0 here. Term is gone. If x is negative 1, that term is also gone. If x is negative 1, we have minus 1, that's negative 2, times negative 1 gives 2, then 2 times b is 2b. Dividing on both sides by 2, we find b to be 4. To find the value for c, we look at the shared factor in these two terms, and it turns out to be x minus 1. The 0 for x minus 1 would be 1, so we let x equal 1, and these terms go out. Let's go over to the left. If x is 1, we have 3 here, negative 7. 3 minus 7 is negative 4. Negative 4 with negative 2 is negative 6. So negative 6. And then let's see, if x is 1, we have here 1 and 1, 2, times 1 is simply 2. 2c on the right. Dividing on both sides by 2, we find c to be negative 3. Now, let's rewrite our fractions. If the a value is 2, then we have 2 over x. We found b to be 4, so we have 4 over x plus 1 We found c to be negative 3, so we would have negative 3 over x minus 1. Instead of writing negative 3 up here, though, I'll make the minus sign the sign preceding the fraction, so we would have minus 3 over x minus 1. This problem contains an interesting nuance. It's the fact that we have two factors of x plus 1 in the denominator. Notice the denominator is already in factored form, so it's a little tough here maybe to see the degree of the polynomial denominator. Well, if we square this binomial, we'll get a quadratic factor. Quadratic factor times 2x would give a third degree polynomial. And a second degree polynomial in the numerator, well, we're okay to proceed as we have before. Now, we remember that our partial fractions take on as denominators all the different factors that we see in this factored form. Only trick here is that we have two factors of x plus 1. And it turns out that we need to have a partial fraction for one factor of x plus 1 and another partial fraction for two factors of x plus 1. So, in other words, the partial fractions will be a over 2x, then b over x plus 1 to the 1 power, and then a c over x plus 1 to the second power. So we have to have a partial fraction for each of the different degrees of this multiple degreed factor. You see, if we had a fourth degree factor here, or a factor to the fourth power, 4 factors of x plus 1, we would have to have x plus 1 in the denominator of one partial fraction, x plus 1 squared in another, x plus 1 cubed in another, x plus 1 to the fourth in another. That's the idea. Okay, now we proceed as we normally would. That is, we want to clear those fractions, and we do that by multiplying through by this common denominator. Common denominator times this fraction leaves the numerator. Common denominator times this fraction, let's see, the two x's would cancel, leaving x plus 1 squared times a. So we have this. Then common denominator times this. One of the x plus 1 factors would cancel here, leaving the other one, you see. So we would have 2x times x plus 1 times b. And then common denominator times this term, the x plus 1 squares would cancel. Then we have c times 2x. All right, now we need to let x take on values that will cause some terms to disappear. The dilemma here has to do with finding a value for b, because look at what happens. B has with it factors that are consistent with both of the other two. If we were trying to find b and we said, okay, let's eliminate c by letting x take on 0, but if x takes on 0, then this goes out as well. We might say, well, let's eliminate a. If we let x take on the value negative 1, then we have negative 1 here, another 0. Well, here's how we handle that situation. All right, first of all, just choose a 0 of any of the factors. Now, I've chosen to find the value of a by looking at the shared factor in these two terms. That shared factor is the 2x. I'm letting x take on the value 0. When x is 0, then, on the left side, this goes out and we have negative 1. And over here, these two terms go out as expected. 0 plus 1 is 1, 1 squared is 1. So a is negative 1. All right, great. Now what about, let's see, what about our other factor? Well, we have, this can go out if x is negative 1. Now these two share a factor, so when I let x take on the value negative 1, I'm going to find the value of c. All right, let's just go through that and then we'll deal with b in just a second. All right, so we let x take on the value negative 1, and negative 1 squared is 1, so we have 4 minus 1, 3 on the left side. On the right, this goes out, and that goes out, and when x is negative 1 here, we have negative 1 times 2, that's negative 2 times c, negative 2c. Divide on both sides by negative 2 to find c to be negative 3/2. All right, now what about the value for b? What are we going to do? Well, notice that we've already found values for a and c. We know their value. You see, all we have to do is choose any value for x that we want to other than 0 and negative 1. Anything we want to, and just fill in the information that we already know concerning both x and the values for a and c, and then solve for b. For example, another value that's really easy for x would be simply 1. Well, if x is 1, then let's see, on the left side we would have 1 squared is 1, 4 minus 1 is 3. All right, that's fine. When x is 1 right here, we have 1 plus 1, 2. 2 squared is 4. 4 times a. Aha, a is negative 1. You see? So 4 times negative 1, that's negative 4 for that term. And then here for b, well, let's see, b is what we're looking for, but x is taking on the value 1, so 1 plus 1, 2. 2 times 1, 2. 2 times 2, 4. 4b. And then over here, if x is 1, we have 2 times c, but c has a value, and c's value was found to be negative 3 over 2. So we have negative 3 over 2 times 2, cancellation, negative 3. And now we have an equation involving b only as the variable. So solving it, we find b to be 2.5. And now we write our various fractions. We would probably set them up like this. Let's see, for a over 2x, if a is negative 1, we would probably write this as negative 1 over 2x. And then let's see, b is 2.5. We would probably think of that as 5 halves. So we would write this as 5 halves over x plus 1. And then the c value is negative 3 halves. So instead of putting plus here, I'll put minus, and then 3 halves over the x plus 1 squared. The new twist in this problem is that in the denominator we have a factored form, but one of the factors is a quadratic factor that isn't the difference of squares here. So we can't factor this further very easily. And, but basically we proceed as we did before. We think, well, our partial fractions are going to contain as denominators each of the separate factors that we see here in this denominator. So we set up that situation. Now, for our numerators, though, the numerator of this first fraction is simply a as expected. But instead of having a numerator that is simply b, we have to, because this is a quadratic factor, we have to set this up as a linear kind of numerator, a linear polynomial, if you will, and it's in the form bx plus c. You see, we have sort of a first degree polynomial up here. Now, we proceed from here in much the same way. That is, we want to clear the fractions and then kind of go from there. And something rather interesting happens toward the end here as well. Clearing the fractions, we multiply by the common denominator. Multiplying the common denominator times this fraction, the denominator disappears and we have x squared minus 1. Over here, common denominator times this term, the x's would cancel, leaving a times x squared plus 1. Common denominator times this fraction, the x squared plus 1's cancel, leaving x times bx plus c. Now we would expand. Now on the right, we have a times x squared, ax squared, a times 1a. X times bx is bx squared, and x times c is cx. Now, we have a little bit of a dilemma at this point. Now, you might say, well, gee, we can just let x take on the value 0. See, x takes on the value 0, and we find a to be, negative 1. You see, if x is 0, this term goes out. So a would be negative 1. The dilemma comes in trying to find b and c, because from there, we're painting ourselves into a mathematical corner. Here's what we can do, though, and it's a very simple idea once you've seen it the first time. You rearrange this polynomial into a form which is basically the quadratic form. Now, the quadratic form is something x squared plus something x plus a constant. And so let's see if we can create that form. We have two terms that have x squared in them. I'm going to factor x squared out of these two terms. I would have x squared times a plus b, or a plus b times x squared. Now then I have a first degree x term, and then I have a constant term. All right, now what we do from here is we kind of compare the polynomials on both sides of the equation. This equation is supposed to be equal, so does it make some sense that the coefficients on same degreed terms should be the same? That is, we have 1x squared here, and we have a plus bx squared here. Does it make sense that a plus b should be equal to 1? Go like this. Yeah, that all makes sense. And there's no x term here, so we could think of this as x squared plus 0x minus 1, you see. So 0x, cx. C then is 0. You see, and then for the a part, the constant over here, has to correspond with the -1. So a is -1, c is 0, and a plus b is equal to 1. Well, we just write those three little equations down, and we have only one thing to solve for. A plus b is 1, c is 0, a is -1. But if a is -1, then here we would have -1 plus b equals 1. Add 1 on both sides to find b to be 2. All right, so now we have the values for a, b, and c, and we can write our partial fractions. Let's see, we have a over x. Now the a value was -1, so this is -1 over x. And then plus, now don't forget that this next partial fraction has to be in the form, the numerator is in the form bx plus c. So let's see, b is 2, from looking over there, 2x plus c, c is 0. So this is 2x for that numerator, and it's over x squared plus 1. Here's another one. Now again, we have a relatively unfactorable quadratic factor here, but it's squared. Aha! So we have to use two techniques in one here. Now, I'm bringing down here. Now, we understand that this multiple factor situation means that we have to have a partial fraction denominator containing each of the degrees 2 and below. You see, so if we have to have a fraction with x squared plus 4, and we have to have another fraction with x squared plus 4 squared. And if this were to the 4th power, we'd have to have one that's x squared plus 4 to the 3rd and x squared plus 4 to the 4th, you see. So it just creates other partial fractions. Okay, so now we set up the skeleton for that situation over here. Now, because of this quadratic factor situation and the quadratic within parenthesis here, the numerators are both in this linear form, this linear polynomial form. And it's ax plus b then for this one. We need a couple of other letters over here. This will be cx plus d. You see? And now let's kind of follow our nose through this one. Common denominator times every term. Common denominator times this term leaves the numerator. Common denominator times this term leaves one factor of the x squared plus 4 times the ax plus b. So it's x squared plus 4 times ax plus b. Common denominator times this term, the nice cancellation occurs, and we have cx plus d. I'm putting in parentheses just for emphasis here. We would need to expand on the right side. X squared times ax is ax cubed. X squared times b is bx squared. 4 times ax is 4ax. 4 times b, 4b. And I'm bringing down the cx plus d. Now, we're going to pick up the problem at this point. What we're trying to do is rewrite this expression in the form of some kind of polynomial that is of some degree maybe corresponding with this, but we have a 3rd degree thing over here and we have a 2nd degree polynomial over here. But we can think of this as a 3rd degree polynomial, can't we? Because after all, we could think of this as 0x cubed then plus this. All right, so that's all right. So let's create terms that are 3rd degree, 2nd degree, 1st degree constant. All right, that's what we want to do. We only have one 3rd degree term, ax cubed. Our 2nd degree term, only have one of those. Now, what about for x? Well, I have an x here and an x here. I can factor the x out of those two terms, and I have x times 4a plus c. Or I can write it as 4a plus c times x. Usually if we're looking at a correspondence to our previous experience with polynomials, then we would write the coefficient to the left of the letter, of the variable. All right. Then we have 4b plus d. Now, 4b plus d is the entire constant here, so I'm thinking of this as one item. And I'm thinking of it as one item, and I'm thinking of all of these coefficients and so forth in order to create a correspondence with the coefficients and the constant over here. And that's all we do, is we just write those correspondences. We have 0x cubed here, we have ax cubed here. Oh, a then is 0. So a is 0. Now let's see what else. We have bx squared here. We have 2x squared here. So b must be equal to 2. We have 4a plus c times x over there, but we have 1x over here. So then 1 must be equal to 4a plus c. But wait a second, we have a value of a. A is 0. Ah, well then 4a means 0, you see. Then plus c. C is 1 then. All right. Then our constant, 8, must be equal to our 4b plus d. So 8 equals 4b plus d. And let's see, we have a value for b. Let's look back over here. Oh, b is 2. So if b is 2, we have 2 times 4, 8. 8 plus d, subtract 8 on both sides, we find d to be 0. All right, now we have values for a, b, c, and d, and we just read them off down here and write our partial fractions up above. Let's come up here and do that. We have, let's see, ax plus b. The a value was 0, so that goes out, and then b was 2, so we have 2 over x squared plus 4. And then, let's see, we have cx plus d. The c value from below is 1, so we have simply x plus d. D was 0, so we have 1 over this denominator. And that's it.